Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to learn a brand new topic under the umbrella of differentiation, and it's called implicit differentiation. And we have three major learning objectives to achieve today. First, we're going to learn how to distinguish implicit functions from explicit functions. And second, once we spot an implicit function, we're going to learn how to differentiate implicit functions, and we're going to use the skills that we gain from implicit differentiation to learn more about the logarithmic differentiation. All right, let's get started. Most of the functions that we learned so far are given explicitly, which essentially means that you are given y on the left-hand side of the equation, and you have the description of the function written on the other side of the equation. In other words, we call it like y is explicitly written as a function of x, but some functions are not provided us in that form. For example, x times y equals 1, so y is not isolated from x, so it's like mixed up in the equation. So we call this form an implicit form. In fact, we can convert this form to an explicit form by dividing both sides by x, so that y becomes 1 over x. So we can sort of like go back and forth between implicit and explicit forms for certain functions. For some other functions, like this one, it's not easy to solve this equation for y and write y explicitly in terms of x. And in fact, if we are required to find dy over dx, and that hides all the information about the slopes of tangent lines, we have to sort of like develop a technique to take care of the derivatives of these types of functions without solving this equation for y. Now going back to the discussion of the function xy equals 1, which is given in the implicit form, we can easily solve y for x, and in fact that's what we did earlier. And once we take the derivative of y with respect to x, all we do is just rewriting 1 over x as x to the power of -1, which is in the power form. So we can use the power rule to find the derivative of that, and that's negative x to the -2, which is equal to 1 over x squared. See, if the function description allows you to solve a y in terms of x, go ahead and do it and find the derivative accordingly. Otherwise, as I said, we need to find a new technique called implicit differentiation to take care of the derivatives of this type of function where it's almost impossible to solve y in terms of x. Here, notice that we're after dy over dx, which means that the derivative or differentiation is going to be taking place with respect to x. So whenever we see a term involving y, then we're going to use the chain rule. This is the key in implicit differentiation, and it's simply because you're assuming that y is defined implicitly as a differentiable function of x. So again, whenever we see a term involving y, then we're going to apply the chain rule for that term. All right, let's have a few practice problems before we dive into the details of the implicit differentiation in the next video. So let's say like we have the d dx of x cubed. That means we're taking the derivative of x cubed with respect to x. This is a kind of derivative we have been working on so far. It's just the application of the power rule, so we have 3x squared. Here the catch is that the variable that you take the derivative on is the same as the variable of the function that you're trying to differentiate. So that's good news when the variables agree, so we just simply use the rules that we have had so far. So now let's stare at this example here. So instead of x cubed, now I have y cubed. So we know that y is a function of x, and whenever you see a term involving y, we're going to use the chain rule. And in fact here, the derivative variable is totally different from the variable of the function that you're trying to differentiate, so the variables disagree. So essentially, you're going to treat this as the cubic power of y, and you're going to take the you're going to use the chain rule to take the derivative of that, or the generalized power rule. So it's like 3 down y of x squared, and the derivative of the inner part, which is y prime, or dy over dx. You can get rid of this x dependence if you want to, and just simply write this as 3y squared dy over dx. But what I'm trying to say here is that this dy over dx, as you see, doesn't exist here because we are taking the derivative with respect to x, and the variable that the variable that the function is on is here just y. So that means dy over dx is tagged alone. All right, that's the major difference between part A and part B. And now let's have another example to finalize this part of the lecture series. So we have d dx of x plus 3y. So again, whenever we take the derivative of x-related term, we simply use the differentiation rules that we're used to. So the derivative of x is just simply equal to 1. And whenever you try to take the derivative of y-related term, so you're going to use the chain rule. Okay, so this is 3 times y, and y has the derivative, if you use the power rule, so it's going to be y to the power of 1, right? So if you look at d dx of that 1 times y to the 0 times the derivative of the inner part, but y to the 0 is always 1, so simply this turns out to be the derivative of y with respect to x. So for that reason, this whole derivative involving mixes of x and y takes you to 1 plus 3 times dy over dx. Wanted to give you one more example just to make this crystal clear for you. So you have d dx of x times y squared. Again, x and y are mixed, but this time it's the product of x and y squared. Obviously, we're going to use the product rule to take care of the derivative of that. And it says that keep the first function, take the derivative of y squared, plus keep y squared, take the derivative of x. That's the application of the power rule. Here we go. Let's use the chain rule for this term here, right? So that's the quantity squared term. So let's use the generalized power rule or chain rule, whichever is convenient for you. So we're going to put the 2 down and subtract 1 from the power and multiply it by the derivative of the inner part. That makes you go 2y dy over dx. Okay, and x is still tagged along. And you have y squared, and the derivative of x with respect to x, that's simply 1. Okay, so now if you continue, then you will have just 2xy dy over dx plus y squared after you simplify the whole expression here. As you see that once you take the derivative of an implicit function, you will see that you will always have terms like dy over dx popping somewhere in the equation, and that's how we're going to obtain dy over dx eventually. All right, in this short video, we learned how to distinguish functions written in implicit form and explicit form. In the next video, we're going to learn how to implicitly differentiate implicit functions to get dy over dx, which is the derivative of the function. All right, I'll see you in the next video. Bye.